SwayamPrabha. Digital India. Educated India.
Good afternoon. In this course we will be talking about propulsion systems. So, this course deals with propulsion, and in this course we will be restricting ourselves to aerospace propulsion only. So, I said propulsion. Now I have introduced a new term, chemical propulsion. Aerospace chemical propulsion is what we are going to discuss in this course. Chemical propulsion, I mean the energy that is converted by burning a fuel is what I am looking at. So, if you look at the chemical propulsion, the energy is stored in the bonds of the fuel and the oxidizer, and when they are broken and fresh bonds are made, energy is released, which leads to high temperature gases, which can then be expanded through nozzles, which we will discover as we go along in this course. So, this course deals with aerospace chemical propulsion. Now, let us firstly look at what are all the systems that are available for aerospace chemical propulsion. Let us familiarize ourselves with some names of systems. In this we also have something known as air breathing and non-air breathing propulsion. In an air breathing propulsion system, what we have is the fuel is only carried on board, the oxidizer we get from the air. Air has 21% oxygen and we use that as the oxidizer. So, air is used as the oxidizer in air breathing propulsion, which is why it is known as air breathing engine. Here we have turbojet, then we also have something known as pulse jet, which is very scarcely used. So, these are the systems that we have in air breathing propulsion. Let us look at the non-air breathing propulsion systems. Here these are also known as rocket engines. So, you have solid rockets, liquid rockets and hybrid rockets. Now, solid rockets is named so because both the fuel and oxidizer are in a solid phase. So, hence the name solid rockets, whereas in a liquid rocket you have the fuel and oxidizer being in a liquid phase, and lastly the hybrid you have the fuel in solid phase and oxidizer being liquid. So, that is why the name hybrid, because it is essentially a combination of these two systems. So, these are basically the systems that we are going to study in this course, and the textbooks that I am going to use, or the reference books that I am going to use, are as follows. Understanding Aerospace Chemical Propulsion by H.S. Mukunda. Then Mechanics and Thermodynamics of Propulsion. By Hill and Peterson. Then you have rocket propulsion elements. By G.P. Sutton. Then elements of gas turbine propulsion. By J.D. Mattingly. And lastly, Propellants and Explosives by N. Kubota. These are the books that I will be following in this course, and some of them are exclusively rocket propulsion textbooks, like Rocket Propulsion Elements and Propellants and Explosives. These are exclusively deal with exclusively rockets, while the rest of them deal with both rockets and air breathing propulsion. Now, firstly, we need to understand that propulsion means to move oneself forward, or to move oneself from one place to another, that is to propel oneself. So, you need energy to do that, and you need a system to take care of this, and that is what is a propulsion system. And as we have described, there are two kinds of systems: air breathing engines and non-air breathing engines. Let us firstly look at when do we use which one. Whenever we require a very large thrust for a very short duration, like in rockets or in missiles, we use the non-air breathing engines or the rockets. Whenever we need a large thrust for a very long duration, like in aircrafts that go from one place to another across continents, then you will use air breathing systems, because in air breathing systems you have the advantage of not needing to carry the oxidizer. So, therefore, it makes sense to make use of the atmospheric oxygen and propel yourself rather than carry the oxidizer also, which is what is done in these rocket engines. And the other application of rockets is in interplanetary missions, wherein you actually do not have any oxygen available. So, therefore, you will have to carry your own oxygen on board to make sure that you can reach your destination. So, these are used for interplanetary missions and for missions wherein you require a very large thrust for a very small duration of time, whereas this system you use for large thrust, long duration, you use air breathing engines. Okay. So, let us firstly look at some history of how these air breathing engines evolved, and then we will go to the rockets. So, historically man has been looking at nature for inspiration to do things, like we do look at birds flying and we wanted to fly. That was our first attempts at flight. So, a lot of the earlier designs always try to mimic the bird. So, people built what is known as ornithopters. Ornithopters are essentially flapping wing devices which will help us stay afloat in the air and all that, or to fly. They were never really successful, primarily because both the thrust and the lift had to be generated by the wings as done by the birds. And given the weight of the human body and the power we could generate by flapping the wings, we were never able to do both, that is, take care of lift as well as propelling ourselves forward. So, both these was not possible, and it took a long time for people to realize this, that it is not possible to do so. And somewhere in the 1799, George Kelly he was the first one to come up with a system wherein the lift and the thrust producing devices would be separated. So, till that time people were having lift and the thrust producing device the same. He was the first one to suggest that they should be different. So, thus came the idea of fixed wing aircrafts. But this was only a conceptual stuff, and the actual flight happened somewhere in 1903. So, it took almost 100 years from the time we conceptualized flying, that is separating the lift producing device and the thrust producing device, to actually fly. And the reason for that was, although we said that the thrust producing and the lift producing devices are different, they had to come up with a thrust producing device, that was the engine. So, they had to wait they had to wait for a lightweight engine which was also powerful. So, essentially they were looking for a engine which had a good thrust to weight or power to weight. Internal combustion engines began to be developed in the year 1960. And Lenoir developed a 2-stroke gas engine, and later in the year 1876 Otto designed a 4-stroke internal combustion engine or IC engine. And in the year 1903, the Wright brothers had an engine of 9 kilowatt shaft power and it weighed something like 90 kgs. So, essentially a power to weight ratio of 0.1 So, very small power to weight ratios of the engines that were developed. Later on towards the 40s, you had engines of the order of power to weight ratio of the order of 0.4 to 0.6, and in the later years it did improve a little. If you look at this table here, I have put together some of the engines here. You have a reciprocating engine plus propeller. Some of these engines produce something like 3700 kilowatt and had a power to weight ratio of 1.36 and a power to volume ratio of somewhere around 0.3 to 0.4. We will see how this engine works here. So, if you look at the engine would be having a propeller coupled to a piston engine So, this is the propeller and this is the piston engine. So, the propeller is the thrust producing device and the piston is the power producing device. So, what happens is when air comes in here, let us say it has a velocity V A, because of the propeller action the velocity of the air behind the propeller increases to V E, and because of this there is a change in momentum which leads to the thrust being produced. So, you have here the piston being the power producing device and propeller being the thrust producing device. So, with this they were able to propel themselves, and as I said, power to weight ratios of the order of 1.3 were also realized. And if you look at the other performance parameter, namely specific impulse, sorry, in this case specific fuel consumption, what we mean by specific fuel consumption is that it indicates fuel consumed to produce one unit of power So, its units in SI units, SI units would be kg per kilowatt hour, kg per hour being the fuel flow rate and kilowatt being the power that is produced. So, it essentially indicates what is the amount of fuel or what is the fuel flow rate required to produce 1 kilowatt. This was about the engines. Now, as I said, you had engines that was producing a lot of power, and if you look at the Lycoming engine that I have shown here in this table, you see that it had 36 cylinders. So, if you look at the configuration, there were various configurations that were possible, like the single row radial or the double row radial, wherein cylinders were arranged along the radius of a circle. So, all of them used to power only one shaft, that is shown here, and as a consequence you had a phenomenally large power because there were too many cylinders contributing towards the power. Then you had the double row radial. Lycoming engine was a double row radial engine, and then you had the inline engine. Now, the one great advantage that the radial engines have in comparison to the inline engines is balancing of the engines is very easy in this case, whereas it is very difficult in the case of inline engines. V configuration also takes care of the balancing part partially, while the opposed configuration takes care of it completely. So, in terms of balancing, one would look for single row radial, double row radial or opposed configuration. So, these were the kind of configurations people used in order to ensure that they got enough power. So, let us firstly look at an expression as to how to obtain the power of such engines. So, power P is given as, I will write this expression and then explain it. Now, K here represents a constant which is either 1 or 0.5, depending on whether the engine is a 2-stroke engine or a 4-stroke engine. Remember, in a 4-stroke engine there is only one power cycle in 2 revolutions of the crankshaft. So, you have n being 0.5 here, whereas in a 2-stroke engine you have one power cycle for every rotation of the crankshaft. So, that is 1 here. Now, n is the RPM of the engine, that is how fast does the engine operate. Typically the RPMs of the engines that we see in regular life are between 5000 to 9000 revolutions per second per minute. Then we have Vc, which is nothing but volume of the cylinder and then we have rho air, which is nothing but density of air, and F is fuel air ratio. I will explain this in a minute. Qf is the calorific value of the fuel. If you are using gasoline or petrol as the fuel, it is around 47 megajoules per kg, and diesel would be something like 44 megajoules per kg, and kerosene, which is an aviation fuel, would be something like 42 megajoules per kg. And eta overall is the overall efficiency of the engine, and this varies between typically 25 to 35%. So, if you look at this equation here, this part here tells you what is the mass flow rate of air that is being ingested inside the cylinder. So, you have this being the volume and this being the flow rate, this being the density. So, you have mass flow rate of air that is being ingested into the engine. F, as I said, is the fuel air ratio. So, F here indicates the stoichiometric fuel air ratio, that is the amount of air that is required to completely burn the fuel. So, if you are looking at any of the hydrocarbons, it ranges between 13 to 15. So, the ratio of for one part of fuel, you need 13 parts of air to completely burn it. So, then if you multiply it by the fuel air ratio, which is nothing but mass flow rate of fuel divided by mass flow rate of air. As I had already said, this part here indicates mass flow rate of air. So, you multiply it with F, you get mass flow rate of fuel into Qf, which is the calorific value of the fuel. So, if you multiply it by the calorific value, you get the energy that is contained in the fuel, and if you multiply it by the efficiency, you get to know what is the energy that is or the power that is in the fuel that gets converted into useful work or useful power. If you notice, the overall efficiency is a very small number, somewhere around 25 to 35. A large part of this energy we lose out in terms of exhaust gas heat, that or the heat that is carried by the exhaust gases. A significant portion of that of the energy of the that is stored in the fuel, something to the tune of 50%, goes in that as the exhaust gas energy. Now, if you look at this equation, one of the ways in which we could increase the power of the engine is by operating it at a higher RPM. So, if you operate the engine at a very high RPM, then you can see that power goes directly as the RPM. So, the power would also increase. So, if you remember, in India we had bullet motorcycles which used to run at somewhere around 4000 to 5000 RPM, very low RPM engines, whereas some of the more recent high performance bikes run somewhere close to 8000 to 9000 RPM. So, when you increase the RPM, you have higher power. So, as N increases, power increases, and then a 2-stroke engine is better than a 4-stroke engine in terms of power. Then the other possibility of increasing power is, if you look at density of air. Now, the density of air at ground level is around 1.2, at sea level is around 1.2. One of the problems faced with by aircrafts operating with piston engine was that as the altitude increased, the density of air decreases, and as the density of air decreases, we see that power also would decrease. So, as rho air decreases with altitude, we have also power decreasing, and this was one of the major problems faced by initial designers, and they were able to overcome this problem by the use of something known as turbo supercharging, which is explained in this figure here. You have a piston engine, this is the piston, this is the top dead center, and you have the valves here. This is the air and fuel mixture coming in here. So, if you can compress the incoming mixture and supply it, then the density of air that is coming in would be larger, and the way to get the power for this was through the turbine. So, you use the exhaust to power a turbine, which then runs a compressor and increases the density of air that is coming in. So, with the increase in density of air, we see that with the increase in density of air, we see power also increases. The other way to increase is, of course, use gasoline, which has a much higher calorific value than diesel or kerosene. Also, if people were to come up with engines at a later date which have very good overall efficiencies, the power produced per liter of engine volume would also increase. Now, because of this problem that people had in terms of power being limited, and therefore, they had to go in for multi-cylinder engines and other things, people were really looking for another kind of engines, which actually evolved from this piston engine plus propeller. But before we go there, let us look at all the applications of the piston engine. So, piston engines very popular till World War II. And their altitude, that is the height at which they could fly, was somewhere around 5 to 7 kilometers, and the speed which they were able to operate was somewhere less than 500 kilometers per hour. So, these applications of this have been limited to unmanned aerial vehicles, basically for surveillance, then you have small single or two seater aircrafts, and also agricultural aircrafts, that is aircraft used to spray pesticides and other chemicals. Now, because of these limitations of speed and height, the piston engine plus propeller was slowly phased out to its next generation devices. Those are known as turbojets. We will look at what are these turbojets. Turbojets were things that evolved from the piston engine plus propeller. Let us look at the brief history of these devices. Frank Whittle was a pioneer who discovered this in 1937. Ground tested the turbojet engine. He was able to ground test them, and he also had patents for compressors and turbines. But although he was able to do this in 1937, and remember the World War II started in 1939, the British did not really pay too much attention to his inventions. He was a English national, and British did not pay enough attention to his discoveries or inventions, and it was the Germans who first flew a turbojet aircraft, an engine powered by a turbojet aircraft. So, first jet engine was built by a German Hans von Ohain in 1939, and if you look at his engine had a thrust of something like 4 kilonewtons, and it had a forward speed of something like 700 kilometers per hour. The English then woke up to the situation and realized that they had to also do something, because if you look at the speed that these engines were able to go at, they were able to go at only 500 kilometers per hour. The engines that were discovered by Ohain here was able to go at something like 700 kilometers per hour. So, therefore, they were pressurized to discovering their own engines, turbojet engines, and in 1941 the British built their own engine called as Whittle engine. So, they had an aircraft built around it, and it was also having a thrust of 4 kilonewtons and a forward speed of around 550 kilometers per hour, and thus developed the turbojet engines. In the next class, we will look at what these turbojet engines are. Thank you.